Hi, I'm Justin Rutledge, and I'll be describing what I did for my final report, which was an exercise in getting a long short-term memory model, which is a kind of recurrent neural network, to work with polyphonic music generation. So the motivation here was, well, first of all, I'm very interested in music, and I'm interested to see how machine learning can be applied to different kinds of musical applications, whether that's raw audio or MIDI files or anything really. I'm interested in pursuing and seeing what else can be done with these large audio data sets. For this particular project, I decided to use MIDI files. And a MIDI file, MIDI is short for Musical Instrument Digital Interface. And MIDI files are essentially an instruction sheet of music information that can be used for synthesizers to produce music. It is the most widely used musical digital interface, and there's a file specification that's maintained by the MIDI Manufacturers Association, which basically outlines how the messaging system works and how it's stored in a file. What I did was I used a Python framework called Pretty MIDI in order to extract the messages from their raw binary format from several MIDI files, and then convert them into something called a piano roll. And here is an example of a piano roll. This is Rachmaninoff's Etude Tableau, Opus 39, number 8 in D minor, represented visually as a two-dimensional matrix, where we have along the x-axis time, and here it's measured in 1/100th of a second. The MIDI files themselves will have a delta time and a duration of different notes and some other information. They'll also have control information and all kinds of other data. But this is a subset of what is in a MIDI file, and it's normalized, and every one of the piano rolls that you'll see here is normalized to 1/100th of a second for each time step. And each time step represents the next element of a sequence in terms of an LSTM or an R and N. The vertical axis represents the pitch value. Here, each pitch represents a different half step of a standard note, and middle C is at pitch 60, which would be right about here. So this is going to be the middle of the piano. And I've normalized this particular piano roll and any of the rest, and really all of the data, between a range of 21 and 109, which is the range of a piano with 88 keys. The time scale can be anything for any particular file, and then velocity represents the softness or loudness of a note as it's being played. So that often is interpreted as volume by synthesizers. It can also be how hard an instrument is struck, but it's part of the piano roll that you'll see here, and it's relevant to the training of the model. All right, moving along. So why did I choose an LSTM? Well, because I want to generate music, and in particular I want to be able to generate that 2D matrix of a piano roll. And I did this by designing an LSTM with two different linear layers, as well as just the LSTM itself defined by PyTorch already. In these two linear layers, one of them is meant to track probability, the other one velocity, or learn from those features, I should say. And the reason why I have two different in here is because I have two separate activation functions. This is kind of a hybrid model and has kind of a hybrid loss function too, as we'll see when we get into the training function. But I'm using both sigmoid and ReLU for each of these different representative layers. The sigmoid function, because as we see in the piano roll here, every single pitch at each time step is represented by an 88 key vector, or an 88 element vector. And every one of those elements can be on or off. And that's important to represent. So I'm using sigmoid to try and capture that. In addition, each element has a continuous value of 0 to 127, represented by the velocity here. I'm trying to capture that with the ReLU function so that we never go negative. It's got to be positive, and I've normalized that data between 0 and 1. Okay, so here are the hyperparameters that I used to train the model. One big issue that I ran into was that I did not have the hardware appropriate to train this model effectively. Once I reached 3 files, I really couldn't train the model on any more. There was just too much data. Once I converted these MIDI files into these piano rolls, as you see, I have three different songs, 3 different MIDI files that I've converted to piano rolls. In these 2D matrices, once you convert these values to floats, even with a 32-bit or even 16-bit float, it just takes up too much memory. because it's across several dimensions, right? So you have not just the time scale, not just the pitch and the velocity as the value that's being stored in this array, but you also have this in, say, 3 dimensions when you introduce sequences and batches for the LSTM. So with one of these files alone, say, Chopin's 12 Etudes, Opus 25, we have 140,000 elements in the sequence, and each element itself is an 88 element vector, and each one of those can store a value between 0 and 127. Of course, it's normalized to 1, so that's not just 8 bits, it's going to be a 32-bit float. Okay, so you can see that this data can become enormous even though it seems like it's relatively simple and easily visualized. That being said, more than 3 files would exceed the 32 gigabytes of RAM that I have available in my system. I've done a few things to try and shorten that, but you can read through it in the paper if you'd like. Finally, I want to get to what the output is. So I've trained the LSTM, and here is a visualization of the output. This is the seed that was used. So I took the first 5 seconds of a song, and you can see that here, and then the output of the LSTM is here. And it seems to have picked up on some of the patterns. Even some of the rhythm, but it's not great. I mean, this is 5 seconds of playing, where something like this is, 25,000 seconds of playing. 2,500 seconds of playing. So obviously it's pretty compressed. But it seemed to have picked up some of the basic features. It's discordant, especially in here. You'll see there's some minor seconds going on. But really towards the end it starts to sound okay, and at the very beginning it's okay. So the model is either underfit or overfit, or a little bit of both. Using this hybrid model introduces a lot of complexity that needs a lot of tuning of these hyperparameters and a lot more training, a lot more data than just 3 files, and a lot more epochs than 1 epoch. I need more hardware in order to really train this kind of model in the way that I would like, and tune it appropriately. So let's get into the code real quick with the couple of minutes that we have left, and we'll transition over there and let you hear some of what this has generated. Okay, second part of the recording, and we are now in the code. I'm just going to run a pre-trained model that I already have available, and we're going to get it to run the evaluation sequence, to generate a piano roll, convert that piano roll into a MIDI file, and then play that MIDI file for you to hear. So here it is. It took the seed from just a file from the data set, and then it generated a new set of data. So here I'm going to generate the MIDI for it, and we'll listen to first what the seed file sounds like, or the seed piano roll sounds like, the first 5 seconds of this song, and then we'll listen to the new data. So here we go. Here's the seed values. So that was 6 seconds, or 5 seconds or so. And now let's listen to what the LSTM generated. As you can hear, it's not great, especially not at first, but it seems to have picked up a little bit of rhythm towards the end in a way that you really can't perceive from this piano roll alone. So it's skipping, fractions of a second to hit notes in interesting ways. The first bit was really complex though, and it seemed to have picked up on especially the cues from this initial seed, where there's a lot of trills where several notes are being played at once, but it doesn't sound bad in the initial seed, simply because it's not just holding down those notes for a long time. I think that if this model had more time to train, we'd get a lot better results, but I'm really happy with how this turned out given the constraints on the amount of data and time available to train it. Thank you.